Hello everyone. In this video we're going to begin to talk about lesson 10, which is inference for categorical variables. So in the past few lessons we've been talking about inference for quantitative variables. So in lesson 7 and 8 we talked about inference, and when I mean inference, confidence intervals and hypothesis tests for a p, a proportion, and then in lesson 9, we talked about inference for a mean. But both of those, the variables that we were looking at, both in the proportion and in the mean situations, were quantitative in that they had units associated with the numbers that we were looking at. But sometimes we're interested in variables which are categorical in nature, such as hair color or eye color or gender, right? And so, can we make similar sort of inference decisions, such as maybe finding some sort of confidence interval or doing a hypothesis test for something about a categorical variable? And the answer is yes, but it's going to look different than what we're used to because there are no units associated with different eye color. And so I can't give some sort of distance from what was previously believed to be true, or we'll have to think of a different way than what we thought about previously, at least. So there won't be any confidence intervals here, but there will be hypothesis tests. And so before we actually get to the hypothesis test for this lesson, we've got to sort of touch on some important ideas that I skipped over in the early chapters, and those ideas are association and independence. Okay, so we're going to talk about what they mean in the context of this course. Certainly you have some idea about things that are associated and even independent. Okay, these are words that come up in the English language a lot, but they mean something very specific in a stats course, or in statistics. They mean something possibly different than your interpretation of them at the moment. So you want to pay special attention to these next few slides. So the inference that we did, both confidence intervals and hypothesis tests, both had a common, they had a lot of common parts, but the real engine that pushes them were the sampling distributions that we learned about in lesson 6. Okay, those sampling distributions really drove all the decisions. Okay, so the steps that I gave you to make it sort of easier on you to go through a full confidence interval hypothesis test may have sort of made that unclear, but the main engine that drives all of these decisions were the sampling distribution. So how I took a sample, how did that sample behave under certain conditions? Okay, that's really what's going to change here, is how we think about a sampling distribution, or what does a sampling distribution look like? Can we even talk about that in this framework when we have categorical variables? Specifically, we're going to look at two categorical variables and how they are associated or not. So we can't tell if a categorical variable is a specific number, because that doesn't make sense. There's no sort of average of brown, black, and blonde hair. We can't really tell an average of those. We can't give numbers associated with those other than the counts. But we can make still a meaningful statement about how the two are related or associated. And so what do I mean by associated? When two variables are associated, the value of one variable affects the value of another variable. Okay, so if those two are linked in some way, then they're associated. So if I wanted to think of hair color and eye color, a seemingly benign example, you may think, are hair color and eye color associated or independent? And I am no expert in biology, but I believe there is some sort of link there, that you're more likely to have, I don't know, if you have blonde hair, you're more likely to have blue eyes. Okay, and so that would indicate that there is some association between the two variables. Okay, and if the variables are not associated in any way, they have sort of nothing to do with each other, or the value of one doesn't affect the value of another, they're called independent. Okay, and independent is actually a very important word in statistics that is studied a lot, but we just don't have time or the resources to get into it. All right, so when there is no association, the two variables are called independent of each other. And so here I have a few examples of things that I usually use in class to indicate association versus independent. So the first is a very famous example that we all know. And if the variables are smoking and lung cancer, okay, it is generally known that smoking and lung cancer are associated variables. So you would ask a person, do you smoke? Yes or no. Did you at one time or another have lung cancer? Yes or no. And the outcome of asking those questions that is probably that you're more likely to have, there is going to be some association for the people who said yes to smoking and yes to lung cancer. Okay, so that's what I mean by association. Smoking affects whether or not you have lung cancer. Of course, you can never smoke and also have lung cancer as well. That's a difference between association and a causal relationship. Smoking does not cause lung cancer because it's not the only thing that causes, because it's not the only thing that affects whether or not a person gets lung cancer. Okay? So it's not a causal relationship. However, there is an association, meaning that if you do smoke, you are more likely than non-smokers to get lung cancer or some sort of lung disease. Okay? And so, sorry for my long, preachy rant there, but those are important things to keep in mind operationally when you think about a problem like this. Okay? Many of them that I give in this class are toy examples that don't really matter, or you don't take away something from them. But I do want you to sort of dig deeper about the questions that I give you and think about the data behind them, or the sort of the situations behind them that may make them more meaningful to you. Now, end of rant. The other example that I like to give of two variables that are independent or don't have anything to do with each other is the type of cereal that I eat for breakfast. Okay, so that's one variable. It's quantitative. And did it rain or not? Or is it going to rain or not? Okay, so those are two categorical variables. And the value of one does not affect the value of the other. Okay, assuming that I don't have some weird thing that if it rains, then I eat some sort of weird cereal. Okay, so we'll believe that that's not true. Okay? It doesn't matter what type of cereal I ate for breakfast. That in no way has anything to do with whether or not it's going to rain. Okay? So those are two variables that are independent, assuming that my choice of cereal is not dependent on whether it rains or not. Of course, it could be, but I'm assuming not, and so they are independent. Okay, so hopefully that made some sense to you, at least a little bit. Okay. So, oftentimes, when we look at these two categorical variables together and we want to view the data in some way, we're going to look at a contingency table. And so, we did mention these contingency tables earlier on in the course, and I want to come back to them now. Right? A contingency table has the ones that we will work with have one variable on the rows. Okay, and so in this table here, I have income. Okay, and they asked, do you have above average, average, or below average income? Okay, so that's a categorical variable. So that's on the rows of this contingency table. And then on the columns of the contingency table, they have the other variable. Are you happy? Not too happy, pretty happy, and very happy. Okay, and so each of these inputs or these cells inside of the contingency table represent how many people responded the combination of the row and the column in their response. So there are 26 people who said that they have above average income and they are not too happy. Okay, so that's how you read a contingency table for anyone who's unsure about that. I know it's been a while since we've thought about contingency tables, but so there it is. And so the question I could be asking, and this is a question that you very well might ask, or at least think about sometime in your life when you have a free moment to think, is are they related? Are they associated? If you have more income or less income, is that going to affect your happiness? And of course, you would think before you look at the data, your intuition would probably say yes. If you are rich, then you're probably going to be happy. And if you are poor, that's probably going to affect your happiness. Now, that of course, that's not always true, but we're not looking at single cases. Statistics is interested in the behavior of a group as a whole. Okay, and so you could try to look at these numbers and sort of think about each of them separately, how they all work together, and does this show support for association? Are they associated or are they not associated? So does this show evidence for independence or association? And so one thing that we could do is we could try to compare the percentages, okay? Because numbers on sort of the number scale, or the count scale, are kind of hard to read, but percentages are much easier. So here, if I divided each cell, each inner thing, by their specific row total, which was on the right, okay, I am making what we called before a conditional probability or conditional percentage, right? And so if you look at these percentages, you will see a sort of pattern occurring, okay? You'll see that a very low percentage of people are above average and not too happy, okay? And most of them are at least on the pretty happy, very happy side, okay? But as you move down to below average, comparatively, as the percentage, most of them are on the not too happy, pretty happy side, with only a small amount, 19%, who are very happy and have below average income. Okay, so that's sort of how you could reason through it. Each row represents conditional probabilities or percentages. Each row forms what is called a conditional distribution for happiness given the particular income level. Okay, and independence would be when those percentages are equal across the rows. Okay, so what would that mean? Well, about the same amount of people who have above average income are going to be not too happy, pretty happy, very happy, as the people with average income and below average income. Okay, so hopefully that made some sense there. The percentages should be the same in every row, or at least very similar, for me to try to think that these things are independent. Okay, clearly they're not. Clearly they're not, and so it's probably not safe to assume that these are independent. Okay, we could also look at plots of these probabilities. Okay, so all I've done is I've taken the probabilities that we had in the last slide and put them as bars on a sort of bar chart looking thing here. And so you'll see that the bars should be the same height for each, in each group of 3, the bars should be the same height for independence. And if they're not, or not even close, then we say there's an association. Okay, and so looking here, it's pretty clear that there does seem to be an association here. Okay, which makes sense operationally in our minds and what we believe to be true in the world. Now, here's a reading assignment, page 517 to 520, that talks about association and independence in greater detail. Okay, so in the next video, we're going to talk about a test for association. So it turns out we can not just compare probabilities, or we can, but that's not sort of the maybe best thing that we can do. Okay, we can do at least something different, which is a test for an association. Okay, and so that's what we'll talk about next time.